Hello everybody and welcome to my presentation for the virtual Bifi PV Workshop 2020. My name is Alex Barrows and I'm the Director of Research at Exawatt. My talk today will be on trends in bifacial cell and module manufacturing, and if you have any questions from the presentation then please feel free to get in touch with me afterwards. For those of you who aren't familiar with us, at Exawatt we provide consulting and market analysis services for industries focused on decarbonisation. Our background is in PV, and over the last few years we've expanded to include coverage of power electronics, in particular the market for silicon carbide, electric vehicles and lithium-ion batteries. We also collaborate with PV Evolution Labs on a solar technology and cost market report focused on providing insights to PV project developers, particularly those based in the USA. Today I'm going to be presenting some data from our module tracker, which is a quarterly update analysing the modules available from a selection of key manufacturers and based on publicly available datasheets. I'll be talking mostly about the trends we see from this work, and I'll touch also briefly on what we think may come in the future. In the last update of the module tracker we included modules from 27 different manufacturers, and this is a selection including roughly the top 15 manufacturers globally by shipment volumes, plus a number chosen because of their focus on a particular technology. Unsurprisingly, since we started our module tracker in early 2018, we've seen significant growth in the proportion of bifacial modules in the dataset, and in particular we've seen this for P-type technologies, where bifacial modules have grown from less than 5% of all P-type modules tracked to nearly 25% of the P-type modules in the latest update. As I said before, this represents the offerings tracked, not necessarily the market share, but it does show how strong the growth in P-type bifacial offerings has been over the past 2.5 years. For N-type modules, bifacial offerings have fluctuated around 40 to 50% of the N-type dataset throughout the period that we've been doing the module tracker. Here we see the trends in module offerings from the summers of 2018, 2019 and 2020. Each dataset typically includes somewhere in the region of 400 module series, though that does vary somewhat between updates. Monofacial monoperc has remained the largest category during this period, and we have seen a steady growth in the proportion of bifacial monoperc. As we've been expecting, mono-BSF has been all but eliminated from the market, and in our latest update there were no mono-BSF modules. Multi-BSF multiperc and bifacial multiperc offerings have also been declining, in line with expectations and in line with Multi's declining market share, which we track from wafer production for our market updates. Now I'd like to look at some content analysis for the bifacial modules in the dataset. Initially here looking at module architecture and glass thickness. We see that the dual glass framed module architecture currently accounts for the majority of the bifacial modules in our dataset, and we expect this to remain the case in the near term. Offerings with this design almost always use 2mm or 2.5mm glass thickness, with 2mm being the dominant choice. For those modules where no frame is used, we see a greater use of 2.5mm glass, as you might expect. We've also seen a slow but steady increase in the proportion of bifacial modules employing a transparent backsheet, and we believe that this will be a significant growth area over the coming years. Transparent backsheets offer a weight advantage over rear glass, and this is accentuated by the ongoing transition towards larger wafer and module sizes that we're seeing at the moment. In addition, transparent backsheets may be able to offer cost savings over rear glass, although the exact evolution of this will depend somewhat on how successful backsheet manufacturers are at finding alternatives to clear Tedlar. When we look at backsheet ASPs and manufacturing costs across the whole market, so including opaque backsheets, we see costs are continuing to decline, but this is being driven more by a move to lower cost constructions than by cost reductions for specific constructions themselves. So there's a question there around whether transparent backsheets will remain a premium product only, or whether we will see cheaper transparent constructions emerge. And if we do see cheaper constructions emerge, then developers will of course need to consider whether they are confident in the long-term performance of these products. And obviously this is an area where initiatives like the PVAL testing program can be very useful. Looking now at the evolution of wafer sizes, which of course is a hot topic at the moment. Here we show this for bifacial monoperc modules over the past year. We can see a clear move away from M2 as the standard wafer and towards both 158.75mm and M6 wafers, And we've also seen the first M12 based modules enter our dataset. We should also be seeing the first M10 based modules enter the dataset later this year as well. And these trends are very similar if we look at monofacial modules instead of bifacial as well. Of course, probably the key metric that we look at in our module tracker is module efficiency. This plot gives an overview of where current product offerings sit for the key technologies, moving from multi-BSF on the left-hand side through multi-PERC, cast mono-PERC, TOPCon, heterojunction, finally IBC. All of the bifacial modules here are highlighted with the red boxes, and each data point represents the mean efficiency of one module series. The cross for each technology shows the maximum module efficiency for that technology, and the yellow diamonds show what we call the production weighted mean for that technology. So this is an average efficiency that weights modules proportionately to the manufacturer's production volume for that technology. So for example, for mono-PERC, the offerings from large manufacturers such as Jinko and Longhi are quite heavily weighted compared to those from a few manufacturers that produce only a few hundred megawatts of those technologies. We also look at the median efficiency as well as this production weighted mean when we're looking at each category. And if we were to plot median here instead of the production weighted mean, we would see some small variations, but nothing that changes the overall picture. Note that this graph does not include overlapped cell or shingled cell modules. We currently analyse these separately. If you were to include these, then both the maximum and the average for mono-PERC would increase slightly. And also worth noting that the data sets for heterojunction and TOPCon are unsurprisingly quite a bit smaller than for mono-PERC, so the statistics for that should be treated with a little bit more caution. One interesting thing that we have seen when looking at module efficiencies from our datasets is just how high the average efficiencies often are for bifacial modules. This is something that we can see particularly clearly here with multi-PERC modules, where the average efficiency for the bifacial modules actually exceeds that of their monofacial counterparts. And this is something that we've seen in all of our module tracker datasets during 2019 and 2020, and we see this whether we are looking at the median efficiency or the production weighted mean efficiency when we're looking at the average. Now, based on a literature review and also discussions with various stakeholders, we believe that we would normally expect the front-side efficiency of bifacial modules to be around 1.5 to 3.5% lower than monofacial equivalents, which are being made using comparable wafers and comparable processing techniques. And that's 1.5 to 3.5% relative, not absolute. The lower efficiency that you might expect for a bifacial module is due to losses from the rear of the cells and a lack of scattering from backsheet in the cell gaps. And the exact value will of course depend on choices around module architecture, for example what the cell gap spacing is and whether any white printed cell gap is employed. And of course there will be some variation due to 5-watt binning of modules, but overall we think that this 1.5 to 3.5% is a reasonable range to expect. Indeed, for the maximum efficiencies of multi-PERC modules, we do see these in line with our expectations, and in all of our data sets from 2019 and 2020 we see maximum module efficiency for bifacial multi-PERC being between 1.8% and 3.8% lower than the monofacial equivalent. So what's going on here? We believe that manufacturers are preferentially selecting only high quality wafers for bifacial production, leading to higher than expected average efficiencies for bifacial multi-PERC modules when compared to their monofacial counterparts. Meanwhile, maximum efficiency behaves as expected because not all of the highest quality wafers are used for bifacial modules. Some of the best wafers are also used in monofacial modules. It's just that bifacial modules are not being made with the lower quality wafers. Now, looking to see whether we see the same effect for mono-PERC modules, maximum efficiencies, again, we see being broadly in line with our expectations, with the bifacial maximum efficiency typically tracking 1 to 2% below the monofacial maximum efficiency. For average efficiency, we've seen something a little more nuanced than with multi-PERC. When we first started looking in detail at bifacial modules, we saw that for the monoPERC modules, the average bifacial efficiency was very similar to the average monofacial efficiency, implying some preferential selection. For example, in early 2019, we saw the median module efficiency for bifacial monoPERC modules even slightly exceeding that of the monofacial equivalents. And if we use production weighted mean instead of median, we found that production weighted mean was very similar for bifacial and monofacial monoPERC modules. Now, at this point, we forecast that this situation was unlikely to continue as a long-term trend, because as bifacial monoPERC modules increase their market share, preferential selection will become less and less viable without making significant sacrifices to average monofacial efficiencies. And we have indeed seen a trend in our datasets, which implies that preferential selection may be decreasing for bifacial monoPERC modules, with the average efficiencies coming more in line with what we might expect. As I mentioned earlier on, we have to treat the conclusions with a little bit of caution because the dataset is not perfect. There may be some other possible explanations, for example, that only best manufacturers are making bifacial modules, but we've looked for things like that in the data and we haven't found support for a conclusion like that. I just wanted to share this with you today to give a flavour of some of the interesting considerations that come up when we talk about bifacial modules moving to be a mainstream technology in the industry. When we start to think about possible future trends in modules, and in bifacial modules in particular, it's worth looking at how the cost of a module is built up. This graph here shows in-house module cost of goods sold, which is manufacturing cost including depreciation, for LONGi. And it shows it for the wafer, the cell manufacturing step, and the module manufacturing step. Now, this data is from LONGi's annual report rather than from our internal modelling, so it represents a blend across all module architectures that the company is producing. What we see is a gradual trend from 2014 to 2019, where the costs of the module manufacturing step are coming to account for a larger proportion of the total cost of the finished module. And this is a trend which is set to continue in the near future as well. There's more room for cost reduction at the ingot and the wafer steps, for example, with polysilicon price declines and kerf loss reductions, than there is room for cost reduction at the module step. The move to bifacial modules leaves wafer costs unchanged and leaves cell costs almost unchanged, but does add cost at the module step due to the need for rear glass or a transparent backsheet, and for dual glass modules, we see a move to PoE encapsulant, which is a cost adder as well. And there may also be some other small cost adders, such as an increase to module size to accommodate the junction box whilst avoiding any rear side shading. So then, for bifacial modules, we see module step costs being an even larger proportion of the total module cost. With this in mind, innovations that reduce cost per watt for the module step look increasingly appealing for all modules, but in particular for bifacial modules, at least if we're considering front side cost per watt. This means that we are likely to see more and more moves towards small cell gaps or overlap cells, as we've been seeing recently from a number of companies. And there is, of course, one wrinkle here, which is that with the bifacial modules, front side cost per watt is not everything. So developers will need to be careful in considering total energy yield as well as simple front-side cost per watt metrics. The next thing to consider about the future is where monoPERC efficiencies can get to, and of course, what comes next after p-type monoPERC. Now, the first thing to say here is that we continue to see monoPERC module efficiencies improving in our datasets for both average and for maximum efficiencies. Now, this is partly driven by module level innovations, such as smaller cell gaps or overlap cells. But even if we exclude modules using these design features, we still see solid efficiency improvements. So despite some reports that I've seen recently that PERC efficiency is stagnating and has been stagnating, this isn't something that we see in our data at the moment. Of course, this will begin to happen over the coming years, and the big question then is what comes next. Now, this is an area where we spend a lot of our time at the moment, modelling costs for both TOPCon and heterojunction manufacturing. At the moment, from our modelling, we believe that large-scale, fully integrated manufacturing costs for TOPCon and heterojunction could become cost competitive with monoPERC in a front-side cost per watt sense in the 2023 to 2025 timeframe, as improvements in yield, metallization and capex drive down the cost premium. Unfortunately, there's not time to go into more detail on that in this presentation, so it's something that we'll have to leave for another talk. With that, I'd like to wrap up. So thank you very much for your attention. Thank you to the organisers for inviting me to give this talk. I hope you found it interesting, and if you have any questions or comments on anything that you've seen today, then do feel free to get in contact with me.